You need dedicated for at least for the control part, like a dedicated HF uplink, so it's just instantaneous, right? There's no latency due to digital processing and stuff. The only thing is you have to deal with noise. I was actually researching like how do like FPV drones get like the best possible latency, right? And they actually use there's like 5 or 6 gigahertz like analog video links, but the only downside is that it's like 240p or whatever, like
Mm,
480p like resolution you can get out of them because
right.
obviously there's only so much information you can put in a given frequency bandwidth, right?
Totally.
But yeah,
How
that's
would that
that's
look? How would
yeah.
that look on a computer screen? Would that be like pretty good or pretty bad on a computer screen?
I'll just you could go to YouTube and change the resolution to 480p, and you can see for yourself. it 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 basically looks like if you when YouTube first came out in like the early 2000s, all the videos were like 480p.
It's not
That
that
that's
bad though.
it's not that bad. You're just not going to be able to pick out things in the background, right? Because it's like everything's like kind of fuzzy.
True, yeah. So there's no way to make the video better quality with the method that you're describing.
Oh yeah, well yeah, you can always make the video better quality, right? If you want to push more data through a given radio link, right, you have to go up into a higher frequency range. But the thing is, it's like the 5 or 6 gigahertz is an established piece of the spectrum to do this with. So you can buy like an FCC certified, receiver and transmitter, and right, and you're good to go. Otherwise,
But
you'd have
then,
to
yeah,
have like a
that
ham
gets
license.
expensive.
Yeah, otherwise you'd have to have a ham license and like do something at maybe 10 gigahertz or above. And now that gets complicated. You have to roll your own hardware. But yeah, it all comes down to the Shannon information theorems and stuff. I forgot the exact name, but the Shannon like the coding theorems, basically how much information can you fit, in a given bandwidth. Obviously you go up higher in frequency, you can put more
More
information in. That's
detail.
what yeah, that's why everyone they're going to like 6G now and like 60 gigahertz bands because you can the bandwidths are wider that you can work with. Um,
Interesting. Yeah, I'm really again, man. I always say it because it's always true. I'm really glad we got you here for the for the
Yeah.
actual
Well, I'm
communication.
just interested in this kind of thing. It's like, the question of like, how do you get a video feed with the best possible latency, right? Obviously, you can't, go through like the TCP IP network stack. You have to do like pure analog, right? Because then it's just, there's no processing involved at all. It's just, nearly
But
instantaneous.
okay.
Yeah.
So we're talking about people only communicate with the control machine, and then the control machine communicates over those bandwidths with the actual robots.
Yeah, so like this is common in drones where they use like HF frequencies. HF being like one to like 30 megahertz, right? That's the high frequency range. Is that frequency range you get the long distance communication because the radio waves basically use the ionosphere to they refract or diffract against the ionosphere and they bounce back down to the ground, and then they basically keep doing this. So like with an HF link, assuming you have enough power, right, that's how ham operators can communicate around the world, right? You can get
That's
like
fascinating.
halfway around the world with your HF transceiver running maybe like 300 watts, 1,000 watts, let's say, just
Wow.
because you can take advantage of the ionosphere, helping the propagation of your signal. Once you get higher up in frequency, you don't have that anymore. Once you move outside the HF band into VHF, UHF, right? You basically it becomes point to point at that point, line of sight, actually, I should say, at that
Totally.
point, and then right, you just don't get that propagation unless you have something up in space like satcom,
Yeah.
right, can work at higher frequencies, but obviously you need something up in space, but that's still a line of sight as well. You just obviously you can have something
It's easier. Yeah.
right above
Not
you.
nothing's gonna block. Yeah.
Yeah, well obviously you need the satellites, but you also need the
Right.
satellite above you at the right time. Then it's like,
Mm.
okay, it's like
You're like
unless you
20 of them.
Yeah, yeah,
Yeah.
that's right. You basically need a Starlink like array, right? So you can always have something. You can always be in coverage, as the Earth rotates and everything.
Or perhaps a low orbit stratospheric balloon.
Oh yeah,
Some
yeah,
of those,
that would work too. You can
right?
use that. I
That's
think.
my dream.
Well, that's
Yeah.
what they did. I think for the LoRa, that LoRa range test that was like insane. They had an atmospheric balloon that they used as
Right.
one of the endpoints.
Such cool stuff. By the way, I hate to interrupt because this is fascinating, but I'd like to say hi to Joe down there. How you doing, Joe?
All right, how's it going?
I see that you joined. Joe, last time you weren't able to control the robot, and I know why now. So my system works really well for one robot and one operator. I think it's just because of my CPU. I'm on a laptop and I'm hosting everything from the laptop, including this call. So
right.
yeah,
That might be the
I'm not hosting the call, but I'm video calling. I'm hosting a bunch of robots and operators. I'm gonna get myself a serious computer so that we can so that I can make some changes to my code and really take advantage of the CPU or maybe even a GPU. That's gonna be a lot more. I'm going to have to do a lot more. It's going to be more complex, but I think it'll be worth it. So Joe, if you'd like to control one of the robots, check out this link right here that I put in the chat, and feel free to take control, man. And then once you're in control, let me know, and then I will take control, and we'll test this out and see if my recent changes ended up allowing two operators to. I'm getting worse latency. Like it's still very usable, and it's still it's like 90% better than last time we did this. I'm just curious if that latency sacrifice that I made for one operator actually allows us to have better latency with two operators. So I guess we'll see. We're live testing right now.
Let's see. Where is that link here?
You can be operator one.
I'm looking for the link. I don't see it.
Oh, really? Let me send it. It'll be in the chat of this conversation.
That's right.
Oh, I guess that's why Eric, are you able to see it? I just shared it.
Let me just check the link. 1 second. Why don't I see the
Let's
chat?
have one person do it first.
I can't, for some reason, the chat's not coming up for me. Oh, here we go. It was just okay.
Joe, do you already have it up?
I had a brief power outage right before I joined, so everything in my house just rebooted.
Oh, that's. I'll tell you what. Why doesn't Eric try first?
All right.
And then I'll try to get in and see if I was actually having. I completely pretty much rewrote this system so that it can be split into two systems, the open version and then the proprietary version. So like I pretty much redid everything. How you doing, Joseph? Being able to get your audio up?
Yeah, I was able to get my audio up. I just had to finish a couple of things around the house, but I wanted to get the recording at least up because I was gonna just try and set this week's meeting to fully public on my channel.
Nice. Well, I think we might be able to play hide and seek today.
Yeah.
If no hide and seek, we'll at least have much better control for exploring my refrigerator in my house than we did last time.
What's the password for the FPV?
Operator one. Oh yeah, and it'll default to operator. The username is operator one. The password's operator one, and we have operator 1 through 5 for this session. Oh, so nice. The next person who logs in will be operator 2, username and password.
Okay, I'll log
level
in.
Security. Let's let Eric log in first, just to make sure that it works for one person. And
okay, so I'm logged in.
Oh, there he is, Eric.
Yeah.
So hold down. You can hold down the keys. If you put a numlock on, how's the latency? Can you share your screen? Would you mind sharing the browser?
Yeah, just give me 1 second.
No worries, man. You're controlling the good. This robot usually has better everything. Just because I don't know why, but the mechanism. I think it's because of the camera. The camera on Robot 3 is old, and the camera on. All
right, can everyone see my screen?
Yes, I see a million votes.
Yeah, I see a foot.
Man. That's amazing.
I see movement.
Are you able to just like kind of drive it? Like if you actually hold down the keys. Yeah, there you go. That's not as good as I'd hoped, but it's not that bad.
Yeah, I think you're going to see way lower latency when you're doing testing versus when we're doing testing.
No, I do it remotely though. I do it from my cell phone network.
Okay, that's fair.
Yeah.
I'm also partly just talking about the sheer distance. Like,
I actually
you know.
I had a family member log on, and they were getting a lot better latency than I was on my phone in the room.
Oh wow.
Oh, well,
I'd
that's
be curious
interesting.
to know more, but yeah. Eric probably knows a lot about that. Look at this. All right, now
Well,
that
you know what you
Eric
got to
is
do?
using it-
You got to test it using a VPN located in India. That's how you.
Yeah, right.
Yeah.
Get some tunnels.
Yeah, because everyone, you're using your cell phone network that probably hooks in somewhere somewhat localish to the internet, right? Whereas like
Yeah.
some way half around the world, you got to go through all the undersea cable and everything.
Yep.
Yeah.
So fascinating. All this
Transatlantic.
Well, now that Eric's controlling it, Joe is next in line, I think.
Yeah,
Joe,
I just exited out.
yeah.
So whoever's
Okay,
next.
let's do Joe and Josephine then. So
Alright.
Josephine,
Yay.
you exited out of the browser completely, Eric?
Yes, exited out.
Excellent. So let's have Joe be operator 2. Josephine will be operator 3. Username
Alrighty.
and password are the same. Oh yeah, either way. If you already are in operator 1 or something, that's fine. Either way.
Okay, I've logged in under
Sure.
operator 3.
Yeah, then Joe, you'll be operator 2, and let's see if we can get both of these things working well.
I don't know if it's. Oh yeah, it's moving.
I'm getting a lot of lag.
Good. Yeah, it didn't work.
Oh yeah, it's, if I hold down the button, it's actually automatically scrolling and moving.
Yeah, like this is
Okay,
definitely
so-
not as bad as last time,
But
but I am
great.
still getting a lot of lag. Yeah.
Yeah, I showed the deans of engineering this morning, and only one of them connected, and it was like really good. But yeah, it looks. I have some more work to do. I have some more work to do to get this the way that it needs to be. It looks like.
Yeah, but this
Gotta
is
go.
still really dope.
That's so cool.
Like, I'm
Josephine, so I
totally
guess you're-
down.
You're trying to. So Josephine, you're on operator 3. You're trying to control it right now, and it's just not working.
Oh, it's working. It's just really. I'll share my screen to show.
You must be
what-
Robot 3 is not moved. So you must both be on Robot 2.
I'm on
I've
robot
been-
2.
That shouldn't be
I've been
possible.
moving around. Yeah, no, I'm gonna
That
go
should
ahead
be-
and show because I am putting inputs in.
Joe, can you get on Robot 3? Let's see if you're both able to work it. Then all I have to figure out is permissions and priorities. Oh yeah, that's really
Yeah,
bad,
I'm
though.
on 3 now. It'll let me switch.
That's just as bad as it was before. Yeah, it's all right, I guess. I got some more work to do. That's pretty cool though.
What,
Yeah,
what is the,
why
what
don't
is-
you? Why doesn't someone? Who's got? Yeah, Joe, can you share your screen because it looks like
Yeah.
Robot 3 is working well now.
Let's see.
Which one's Robot 3? Is Robot 3 the one with the funky wheels?
Robot 2.
This is robot 3.
Mechanism drive. Robot 3.
Oh, now it's not letting me control it.
I think Joe stole it from you.
I think.
I hijacked.
I'm gonna-
Joe's got great latency.
There we go. Okay, I just
Yeah.
popped over to Robot 2, and now it's letting me control it.
Oh, okay, so we got both of you controlling.
Yeah, now I went and checked the side because you have this handy little thing. And Robot 3, which
Yeah.
was highlighted, said in use. And I'm like, okay, well, I'm going to go on ahead and click on Robot 2. Hush now. My dog is getting very needy.
So it looks, it looks like it's better than last time, but not perfect. It looks like.
It's
Yeah, last
definitely
time
better
I
than
couldn't
last
really
time.
control it that well. It was really intermittent.
Hey, you bumped into me. I'm going to have your license for that.
Where are you at? I'm gonna charge you down here.
Look at it. Look at this. Oh, dude, that is so cool. Look at this. We got two. Where are you located, Joe?
Ohio?
So we got Joe in Ohio, Josephine in Washington, is it?
It's Oregon, but close enough.
Oregon?
I think I'm stuck on
Oregon
the
and
wall.
Ohio. Here in my place in Oaxaca, Mexico, driving these robots, man.
This
That's
is so
pretty
cool.
crazy. And I'm not at my normal. I'm in Oaxaca right now. I've been here for like a month. but we are literally like we are all in completely different places, and these robots are working, man. I'm excited about that.
That's
The
it.
joys of the internet. Where's your cat?
Where's the
I
fridge?
got yeah. Yeah. Check out the feel free to raid the fridge. Eric, while we're playing around with this, and please continue sharing your screen, Joe. I want or whoever's sharing their screen, please continue.
All right.
Eric, how is it? And I know like partially the answer to this, but I think you know the answer and can answer this a lot better. How is it that we're able to control this in real time, considering the fact that everyone is in different countries?
Even different states.
Yeah, well, yeah, different states, and then me like way like south of the border even. How is it that this is all working like this?
That's just the internet, right?
Yeah, the internet.
Yeah, it's sending commands to a server, which sends commands to your local machines.
Well, how is it that the signal like moves so quickly through? You were talking about underwater cables.
Yeah.
I would love to hear some elaboration on
And
that.
isn't
from
that the
somebody.
Atlantic?
Well, you have to understand that everything is fiber optic and
Yeah, I was gonna say, isn't it like fiber optic, the speed of light?
it's fiber optic. It's also multiple fiber lines, and it's like if you look at the internet backbone, it's like 400 gigabit per second bandwidth that they're getting, right? So you have, right, the packets, some TCP IP or TCP packets going, to your router. I assume you have cable internet, or maybe you have FiOS, you have fiber optic. It's going to your ISP. Your ISP enters into a peering agreement with other ISPs and perhaps some data centers too, content delivery networks like Netflix and stuff, right? They peer, and then they have sort of a central, they come together, what's called the internet exchange, right? An IXP, right? And then, the IXPs have agreements with, I forgot the name of that. There's like another sort of like the providers that do, that run and maintain the undersea cables and stuff like that. And they basically allow connections between internet exchanges. If anyone knows the term, feel free. I could just Google it too. But yeah, it's right. You just have different tiers, right? You have your ISP and then the internet exchange. Yeah, the brokers. Yeah, the data brokers or whatever.
So, Emilio, I'm noticing that I'm getting a bit of right drift when I try and move forward on my robot.
Issue. That's
okay. I was gonna say.
Yeah, that's not software. That's
I didn't know.
That's just the cheap Chinese tank tracks that I bought.
Because if that's something that's like a mechanical thing, I'm not sure if you were aware of it. I wanted to let you know what I was noticing.
Yeah, no, I appreciate that. And you know what? Time is flying because we're having fun. Eric, I think you said that you had some really cool stuff to share, and I am fascinated. You said you got your SLAM algorithm working?
No, not working. It's still in the early stages. Basically, I can show you what I've done. I did the research on how basically to architect everything, because SLAM isn't just one piece. It's actually, there's multiple layers involved, right? So you have to architect everything in the right way, so you end up with really accurate pose estimation right at the end of the day. So yeah, I can hold on. Let me just download. I'll share these. They're really like a block diagram and an architectural diagram. Let me just save them.
And guys, what he's talking about right now, state estimation, pose estimation, SLAM with different sensor fusion, this is all stuff that I recruit people who know how to do.
Oh.
So what we're hearing from Eric right now is very valuable information that is going to very much come in handy when we all get our robots built and we start taking this to the next level. This is what we're going to be working on. So Eric's kind of a step ahead of what we're doing right now.
Yeah.
So pay very close attention.
Can everyone see my screen?
Yeah.
Okay. Let me just go to, where's my documents? I did this up at work. Yeah, this is sort of again, it's not actually solving, just as a disclaimer, it's not actually, don't have a working SLAM algorithm yet. It's basically how I'm going to architect everything to achieve SLAM with the required accuracy, with the required precision, and have, as little latency as possible. Right.
Can you scroll in a
So,
little bit?
let me actually turn my screen resolution down. I have a 4K monitor, and I know everyone doesn't necessarily have a 4K monitor. So let me. Yeah, I always forget that because I have to do it during Teams meetings too. Yeah, at work when I'm sharing at home. Okay, can everyone see better?
Yeah.
Okay, so I think I talked about this last time. Well, it's just Joe or Emilio and another guy and myself. Yeah, we talked about sort of this hybrid architecture where you have a microcontroller, which is the Renaissance RX66N. You may be wondering why I chose this microcontroller. It's something I'm using, and we use a slightly different one in a product at work I'm developing now, a gateway. So it's an RX66T that we use, but the dev board I have is the RX66N. Where this is relative to other microcontrollers is it's sort of a mid-range microcontroller. So if you're familiar with the ARM like series numbering, it would be like an F4 and an F33, right? A mid-range microcontroller. So it has some features that are necessary to support the math involved to do the sensor fusion, which would be done on the microcontroller. The Raspberry Pi would be actually running the SLAM algorithm, which involves not just SLAM algorithm as in the graph estimator, but there's deskewing, and there's also sort of the I'm forgetting the term. It's in my other architectural diagram. The iterative closest point, that's to basically align the LiDAR readings. But going back to this, you see I have on my microcontroller most of the sensors and actuators connected to it. So I have the two motor controllers. You may be wondering why there's two. Basically, each one controls one side of the robot. Obviously, you can control both sides independently with just one 298, but again, being cautious as I am, I computed the stall current of each motor, and it was around like 250 milliamps. So the stall current is like the worst case current draw that I could have, and the 298 and can it maxes out around 1 amp. So if you have 4 motors at their stall currents, you're right at the margin, right? So as a safety thing, so I don't burn out the BJT and the motor controller, I have 2, right? And then I also have what sort of peripherals they require from my microcontroller. So it's pulse width modulation and GPIO, right? That's the enable. It's just GPIO, and obviously the speed is governed by the PWM signal. I have, each wheel has a wheel encoder. It uses a optical disc and a photo gate, and photodiode, photo gate. So basically every time the wheel spins, it generates a certain number of pulses which correlate to a speed, right? So each wheel has each wheel has its own wheel encoder. Then there's a micro servo that the LiDAR is mounted on. So it's a 180-degree sort of rotation that the microservo can do. So that's how I can do my LiDAR scans. I can show you a picture of what this looks like later. And then also connected to the microcontroller is a 6-axis IMU, integrated motion unit. So that has an accelerometer and gyro. Each has 3 axes. And then there's also a separate 3-axis magnetometer. The reason that's separate, because you can get a 9-axis IMU that has an accelerometer, gyro, and magnetometer all integrated. The reason that I got a separate magnetometer is that you want to place the 6-axis IMU sort of in the center of your RC car to get the best accuracy. You don't have to do any sort of correct geometry corrections. You don't want the magnetometer in the middle between the 4 motors, just because a magnetometer is highly sensitive to magnetic fields. A motor, right, is producing an alternating magnetic field. So the magnetometer is basically placed as far away from the motors as possible. almost like a car antenna would be, just so it doesn't it doesn't pick up the noise, the inductive noise from the motors. And then the Raspberry Pi is separate, of course. It communicates with the microcontroller over UART, which is just a serial protocol. And then there's also a GPIO pin that's used as part of the LiDAR scan to basically synchronize the Renesas microcontroller with the Raspberry Pi. So when the LiDAR scan starts, it's going to fire off, it's going to set this GPIO pin to high, letting the Raspberry Pi know, hey, I began a LiDAR sweep, mark this using your internal timer and use that as the basis for synchronizing the data, the telemetry data being transmitted. I'll talk more about that soon when we get into the architecture. And then on the Pi side, there's the USB webcam, and the actual LiDAR sensor data is also going directly to the Pi. So that's why I have this split. And yes, you could hook up everything to the Pi, but you'll see why the microcontroller is superior, because I can get very precise timing deadlines that I cannot. This was something we were talking about last time, Emilio, was just the fact that
RTOS.
Yeah, with RTOS, it's not, the architecture I have is not necessarily, it's a real-time architecture, but it doesn't use a real-time OS because it's just unnecessary. But I'm able to meet very precise timing deadlines. You may wonder why that's important. So one example would be like with motor control. You may be using the Raspberry Pi's PWM to control a bunch of motors. But let's say the Raspberry Pi, ordinarily you would have it running as like a single core, and you can do some fancy stuff, right, to like preempt things and use the real-time patch. But ordinarily, like if you have like a Python script driving, motors by providing a PWM signal, like, you get like a incoming Wi-Fi packet, or you get an incoming mouse interrupt, the kernel has to stop what it's doing and process those things. So you actually end up with jitter. And, maybe this isn't a big deal, with like low, sort of,
just robots.
Yeah. If you had like a drone, right? The drone, if it had to process an interrupt for something like a mouse event, which you wouldn't have a mouse connected, but say it's got to process an interrupt for like some kind of like communications, commands, right? It's got to, basically the servos are going to stop, and because again, the PWM signal is lost. So by having the motor controllers hooked up to my microcontroller, I'm able to, ensure that my PWM signals are continuous and there's no jitter at all. Like, it's everything is nearly real time, right? And then the other thing too, when you're doing sensor fusion, especially for SLAM, timing is also very important, right? Because you're as part of this, which we'll get into when I show you the architecture, you're doing dead reckoning, where you're actually integrating. You're using Newton's equations of motions, right? The x plus vt, the y plus vt for the y coordinate. And you notice there's a delta t in that. If you have jitter and your timing is off, you're going to have degraded accuracy. So the microcontroller, like I said, on the motor control side, lets me get smooth, reliable control of the four motors. And then also on my sensor fusion for SLAM, I'm also able to get very accurate position measurements and correlate them with a known time, and everything matches up because there's no jitter at all, because again, there's no Linux kernel that has to process different interrupts, right? The Linux kernel's, on a Raspberry Pi, is constantly being slammed with interrupts. Anytime you move your mouse, that's an interrupt. Anytime you press a key, that's an interrupt. Anytime there's a Wi-Fi packet, that's an interrupt. So it's constantly, any kind of script you're running on the Raspberry Pi, it's got to constantly keep pausing and pausing and pausing, which again, for simple applications is fine, but when you need like something like a drone, you just can't have that. It's unacceptable. So that's why we have microcontrollers.
Yeah, definitely.
Yeah.
I have a quick question, Eric.
Sure.
Was there a specific reason you went with the L298N and not the TB6612?
It's just the first thing I saw on Amazon. I plan to replace it with the one you mentioned that has the MOSFET, right? Because the biggest issue with the L298N, as you know, others may not know, is that the L298N is based on a BJT, a bipolar junction transistor, and it has that voltage drop that causes you to lose essentially speed, right? Because voltage is related to speed. So if you're feeding the L298, say with like 7 volts or 5 volts, you're only getting like 3 volts out. That your motors are only seeing 3 volts because you have like that 2 volt, that 1.5 to 2 volt drop at the transistor junction. Whereas with the MOSFET based one, the DRV, I forget you know, Emilio, that
TV6612.
Yeah,
I only know because I've been constantly.
So that uses a MOSFET, and there's a small voltage drop at the junction of the semiconductor, but it's not as bad as what it is with the BJT. So yeah, you definitely this will get swapped out later, but I'm probably going to keep the 2 independent ones just so I don't. Again, I'm counting for my stall currents and making sure that no matter in any situation, if it's going to be very rare that all 4 motors would stall at the same time, but that's kind of the safety factor you have to think about is what's the worst case scenario, plus I need some headroom. So if I'm at the stall current, I'm drawing 1 amp, which, the L298 or 298N can support 1 amp, but again, I want headroom. So that's why it's going to be at most, the worst case draw is always going to be 500 milliamps on each one. And I got that 500 milliamps of headroom too, just in case my calculations or I should say my measurements off. So yeah, that will get replaced. But yeah, so in the final architecture, and then I'll mention one thing too that I was thinking about, which is going to involve more complications, would be instead of having a Raspberry Pi, and this would be like a good low cost option, you connect the Renaissance, or you could actually replace this with something like an ESP32 that has built-in Wi-Fi. Is you could have ROS2, say, running on a laptop, and then you could have your microcontroller, if it's got Wi-Fi somehow, either integrated or external to it, it could just use the Wi-Fi to talk to your ROS2 instance. Yeah, and you only need the Raspberry Pi. So this would be like a great low-cost option because you can get this microcontroller for like $20, like a dev board. Right, a lot of the microcontrollers that can power this you can get for $20, so you don't have to pay the $100 for your Raspberry Pi. You can get something for $20, and you can make it so it can talk. You could run micro ROS, that would be one option, or you can just get the same sort of communication protocol that micro ROS expects, and then it can talk to ROS. It can basically act as a node that can publish and receive commands, publish data and receive commands, right, that the ROS2 architecture expects. So
you get a lot better battery life too, right?
Oh yeah, that's another thing too. Yeah, you're unlike the Raspberry Pi, which if you were able to strip everything down from Linux that you don't need and get a very lean and mean custom Linux distro, you're looking at the best, it's about 400 to 500 milliamp draw. So with this Renaissance RX66N, since we use it at work, I know the draw is essentially about like 20 to 50 like milliamps. So it's like 10 times, like even the best case Raspberry Pi scenario where you make a very stripped down Linux distro, I'm able to get 10 times better, current consumption. And then the other thing too that you can do with microcontrollers, you could kind of do it with a Pi, but it's not designed to do it. The microcontroller, you can have it so it's interrupt driven, which means that unless it's actually receiving an interrupt, it's just going to stay, in a low power mode, right? It's almost like putting your computer in sleep mode. So say it receives an interrupt due to like a command it receives on the UART from the Pi, it can just conserve battery. So that's another important technique that you can do on microcontrollers that you can't really do with a Pi. I'm sure there's a way to do it, but it's just not really designed. The Pi is designed to just run continuously, right? With the microcontroller, it's designed to stay or spend most of its life sleeping, waiting for an interrupt on one of its pins, right? So that's another important advantage Amelia pointed out. So any questions till we move in, before we move into the architecture? Okay, so this is the architecture, and some explanation is needed, right, for this. But this is basically what I'm going to look to essentially code this. So it shows you how the sensor fusion
I'm
works.
sorry, Aaron.
Yeah.
Could you scroll in? I feel like
I'm just gonna talk
section. Yeah.
I can do that. Unfortunately, it's a little blurry. I should have exported it at a much higher resolution, but yeah, you can see it.
Great.
Yeah. So actually, let me start at the bottom. So with a microcontroller, right, the starting point is always a infinite while loop, right? That's what microcontrollers do. If you ever used Arduino, right, you're always greeted by that while one, right? That's an infinite while loop, and basically every microcontroller, is a variation on that. Even if it has a sophisticated schedule, there's always some, main loop, an infinite while loop that is doing some work in the background. In this case, my main loop is pretty stripped down. So the main loop in this case would only look for any commands that come from the Pi over UART. I would check the battery voltage because this assumes that I'm using a separate battery pack for the microcontroller and the motors. And then it would also just blink an LED. So there's actually not much being done in the main loop. The reason is that most of the heavy lifting is done outside this main loop. And why? So here's actually the magic of microcontrollers that you just can't get with a Pi. You can kind of get these things, but they don't come easy with a Raspberry Pi. But this is what makes the microcontroller a true real-time system. So you see here up at the top, I have high-speed interrupt. So folks may not be familiar with the concept of an interrupt, but here this would be something it's a hardware timer based interrupt. So a hardware timer is a clock, and a microcontroller has several of these, depending on how expensive it is and where it is in the tiers. But there's a bunch of independent running clocks, called timers that are inside this microcontroller. And what this allows me to do is basically make tasks run at a very specific time frame, right? So here at the top is this high-speed interrupt that I'm essentially, again, I'm not sure if I'm going to be able to achieve this timing. I have to actually run the math, get the data and run the math and see if I can accomplish this, in essentially every 2 milliseconds, right? Let's say it takes 4 milliseconds. Well, I have to, adjust the timer accordingly. But essentially what I would have is a hardware timer, and every time it gets up to where it overflows, right? And you can change the period of any timer in your configurator tool for your microcontroller. But essentially I've configured this to time out once it gets up to 2 milliseconds, right? It's going to count up to 2 milliseconds and then fire off an event. So with this timer, what it does is once it overflows, once it gets up to its maximum, right, it's going to initiate a callback. So I'm actually going to have all of this that you see in this dotted box be part of my callback associated with a timer. So again, this is something that's independent of this main loop. And that's, again, how you get this real-time functionality is that you don't, put these things in the main loop. They're always associated with a timer as a callback once the timer overflows. So, again,
me if I'm wrong.
Yeah.
Just to make sure we're plain English, and correct me if I'm wrong. So you've got your while loop that's incredibly simple. It's happening. Yes. It's just while true. In this case, while one. Yes. And then all these other systems, all these other processes only happen when they need to. Whereas on the Pi, they would be constantly trying to happen. That's how we actually get that lower latency and that use.
But that's the thing is on the Pi, they can't constantly happen because it's constantly being interrupted by the kernel. So, when actually,
so it's ultra efficient.
Yeah, well, this is the only way that I can actually get something other than implementing it in actual silicon to actually get something to run when I say I want it to run. God damn it.
Yep.
Right. This is the only way you can do. Again, you can kind of do some magic with the Pi and using the real-time patch, and you can set like priorities and stuff like that, but you still got that kernel that you have to fight with. And the kernel is constantly being interrupted. So like when I have these hardware timers and I associate callbacks with the hardware timer, I'm actually, and assuming like I can actually achieve, because not, I can say that I want this to happen every 2 milliseconds at 500 hertz. Again, if for some reason it takes like 3 milliseconds, I'm going to have to adjust my timer accordingly. But let's say, I implement this math, to do this on a microcontroller, and I'm able to achieve this in say like 1.2 seconds, then I'm actually able to, and also I also have to check that no matter what the input is, that I'll also be able to achieve that. This is like the worst case timing for an input. So assuming I do that analysis, I'm actually able to actually, have guarantees when things happen. Whereas with a Raspberry Pi, you can't have guarantees when things happen. So, so like I said, this is my high-speed interrupt. And you see at the top here, I have the 6-axis IMU, the 3-axis magnetometer, and then the 4 wheel encoders. So a lot of, the wheel encoders are GPIO, so I can sample them pretty much instantaneously. And then these two are on the I2C bus. So whatever the clock is, say it's like 1,000 hertz sampling rate, basically I'm able to grab this data faster than I can do this interrupt, right? Because that, obviously if it took longer than my interrupt, then I'd have to adjust my interrupt accordingly. So let's say I can sample these things at 1,000 hertz. The first thing I'm going to do is there's actually multiple layers of sensor fusion going on. I'll say this too. It's just not like one sensor fusion. So the first sensor fusion is this Magic filter. And this Magic filter is, we can look it up really quickly. It's something I came across. I don't fully understand the mathematics. Of course, it's not really important to fully understand the mathematics, but essentially uses quaternions and uses gradient descent to take noisy IMU data and come up with a good estimation. So I found that this works really, from what I read, this works really great on low power microcontrollers. So again, until I actually implement it on my microcontroller and do the timing analysis, and by timing analysis, what I usually do is I'll put I have a GPIO pin fire when a certain block of code executes, and then I'll look at it on my scope, and then have a GPIO pin fire again when it's done. So this is actually how you can also do it with software timers, but it's not as accurate, and having it just, do like the delta, that you do like on your PC, right? When you want to do like timing, when you want to do like code profiling, you'll have like the timer start right before the section that you want to profile, and then have it, stop at the end, compute the difference, and then display it. If you really want like real accurate results that aren't like rounded or anything like that, you actually just have your code fire a GPIO signal, raise a GPIO pin to high or low, whatever, and then look at it on the scope and, use the markers on the scope to compute how long it actually took.
I hate to interrupt,
Sure.
Eric. This is all fascinating stuff, but I know that Josephine has work. Do you guys have any questions? Next meeting is going to be the meeting where you guys tell me what you need in order to get your robots built. I would prefer that you guys can do that, and then we can meet up to take care of the software stuff, which is really where the heart of this club lives. But next meeting, if you guys still need help building the robots, I'm going to be there for that, just so you know. But does anybody have any questions at this point about all the fascinating stuff that Eric has put together for us in terms of the architecture?
No questions. This is all seeming very interesting.
Yeah, it really is. And this, again, everything that Eric is going over here, this is what the industry needs. He's using, I see accelerometer, gyroscope. I don't know if you were thinking about this, Eric, but you have a system. This system that you're describing has the potential for visual inertial odometry, which is a huge, very in demand right now.
That's actually what the system is.
Yeah.
So let me
people who could do this.
Yeah, let me just sum up like this real quick.
Totally.
So yeah, I'm using the magic filter as like my first pass at doing sensor fusion. What I'm getting out is the absolute yaw, right? So that's basically my heading, right? Theta. And then the yaw rate I'm getting directly from the gyro. That's how fast it's spinning. And if you think about the z-axis as pointing up from the floor, right? How fast it's spinning in that axis, the rate of rotation, right? So all this, so the magic filter, I can, assuming, again, looking at the math, I assume I can do it relatively quickly in this high-speed interrupt. So what I can do is use, like I said, as a first pass, and then the wheel encoders, I average them all together to get a linear velocity. I don't use the wheel encoders to get any angular velocity because the IMU is much more accurate for that. So you could get the, using geometry, get the angular velocity too from the differential velocities of each side of your car, but I don't do that. So again, I have another timer that's much slower timer, and this is actually where the extended Kalman filter comes in. So the extended Kalman filter is you make a prediction based on a kinematics model, basically using Newton's equations of motion, and then you update it based on something that you believe is a very accurate measurement, which is this absolute yaw that comes from the magic filter. So this is much more accurate than just the raw heading information that I would get from my IMU. So I'm using that to correct my prediction. And the Kalman filter, the mathematics is kind of complicated, but what the Kalman filter will do is it will figure out, it's basically a tug of war between how much weight that you put on your prediction and how much weight that you put on the measurement, right, to correct the prediction with. So it's actually going to balance your prediction with the measurement and basically fuse that information together to make a more accurate estimation of pose. And by pose, I mean the XY coordinates of where your robot is relative to some initial location, right? Basically, wherever the robot, you turn on the robot is going to be 0, 0 in your reference frame. So by pose, I mean XY and then your theta, which is your heading. Right, that's the three things we're interested in predicting. And then also inside this control loop is my motor PID control. So it would use a proportional integral derivative controller to, actually get a accurate speed from the motors, because the motors, don't exactly move at the same rate and everything too. Go into more of that some other time. And then there's the micro servo control, which is where the LiDAR is sitting on. And then once it has all this information from the extended Kalman filter, it's going to send it to the Pi over UART. So it's going to send its XY, yaw, linear velocity, angular velocity, servo position, and timestamp to the Pi. And then the Pi, I don't really understand this at a low level, but I'm just going to use a library. The Pi is going to have the LiDAR sensor sweep data. It's going to correlate it with the telemetry data from the Pi, and since the robot's moving as it's sweeping, it's got to deskew the LiDAR measurements, basically make it so as if the robot was stationary the whole time. So it's got to use the telemetry data to figure out how to correct the LiDAR measurements to make it as if the sweep happened when the robot was stationary. And then it's going to use iterative closest point, which is another algorithm that I don't understand all the details, but basically, once it does a LiDAR scan, moves to another location, does a LiDAR scan, it's got to connect those measurements together. And iterative closest point is the way to do it. And then finally goes to your graph optimization algorithm, which sort of had a video that really explains it well. I'll just put this link in the chat just because we're running out of time. But basically, the idea is that you do LiDAR scans at each of these points, and then you close the loop, and you basically assign different weights to the edges, and then you're able to post-correct, your earlier predictions. So just to summarize, it's like we have sort of different tiers of pose estimations all going on simultaneously. We have sort of the raw readings, which are noisy and inaccurate. They're subject to drift. We do one layer of correction with the magic filter to get an absolute yaw. And then every 200 milliseconds, we have this extended Kalman filter giving a better update of all these variables. And then finally on the Pi, because you can't do this on the microcontroller due to the processing constraints, you run the graph optimizer once you do the initial processing of the LiDAR scan. Then you're able to get even a better estimate of your pose. So we basically have 3 layers that are, each layer from the bottom runs quickly and gives you sort of a crude approximation, and then you keep refining that until you get all the way to the graph optimizer. And that's just how this architecture works. It's just a tiered architecture that really takes advantage of the timing, the careful timing, meeting careful timing requirements on the microcontroller, and then using the Raspberry Pi as the brain to handle the very heavy lifting that just wouldn't make sense to do on your microcontroller. So it's sort of best of both worlds.
Josephine?
Huh? I didn't say anything.
Oh, I saw your thing light up. Oh, yeah.
Oh, that's probably because I coughed.
Yeah, no worries.
Yes,
Eric, I'm going to get this meeting. This is not a meeting I'm going to edit. This is going straight up on YouTube. Everything here is so valuable, and this is a work of art you've put together, Eric. I'm very impressed. This is great stuff, and this really is the next step for us. So after we've gotten to the point where we have our robots and we're ready to go, we're ready to program, the next step is what Eric is doing. Eric is doing exactly what it is that I want to take this group toward. And I didn't talk about this with him. It's kind of crazy, but yeah, Eric, you read my mind, man.
I just uploaded the block diagrams to the chat. So again, it's very preliminary, so I just want to talk about the next step for me with actually not being implementing this on hardware. It actually makes much more sense using a shift left philosophy of making a digital twin of these sensors in Python, and then using
Gazebo. Yeah, just so everyone knows.
Yeah.
That's the Gazebo.
Oh yeah, you could even do that too. I was just going to make a digital twin that ran in pure Python, but yeah, you could do that too.
Oh, okay.
Yeah, the biggest challenge to this.
Make a digital twin with no simulation.
Well, you said you use Python, pure Python to do the simulation. Basically, I can easily, sort of mock a bunch of noisy sensor data. That's basically what it comes down to. So yeah, I was going to say the real challenge is getting the mathematics right. You don't want to try to do this in C on the microcontroller itself. You want to make sure you get the algorithms right in Python in a higher level language before you switch over to C, because just experience doing DSP, I would always prototype the DSP algorithm in Python and then transfer it over to C++, just because it's like, you end up like a lot of times seg faulting or stuff like that. And it's like, if you don't even have the algorithm worked out, it's like sucks to try to both do the math in C++ and get the algorithm correct at the same time. So definitely want to have like a digital twin and just do it in Python, and then move over to, you can even before you put it on your microcontroller, you can even use, translate it to C on your computer and also run the C with the digital twin, and then eventually transfer it over to the microcontroller. So it definitely requires a lot of steps, because the math behind a lot of this is not easy. You have Jacobian matrices with the extended Kalman filter, and then you have quaternions, and then you have the graph algorithms with the graph estimator too. So a lot of math, but I assume, for me, I'd be using a library on the Pi side, and the ROS 2 provides some libraries to do SLAM, but the extended Kalman filter and everything else, you really have to code yourself on the microcontroller.
An extended Kalman filter, by the way, guys, is one of the main things that I look for people being able to implement in order to get them jobs with my clients. So at Eric's level, once you understand and are able to implement that, you're going to be looking for a job that's probably going to be paying you over 6 figures.
Yeah, I'll just mention too.
You'll break 6 figures.
I was a math major at SNHU, so I don't even understand all of it myself. It's important to come at it. Just a disclaimer. To me, it's more important to think about it from a systems engineer point of view. It's just like, okay, like what's the input? What's the output? And just understand the gist of what it does and what it requires. So it's like the Magic filter. It's like I didn't even bother. I understand, right? Just reading the literature that it's a good algorithm for correcting IMU data on a low power microcontroller. It's like, maybe it's if I have time I can go into the math, but it's really just understanding. Okay, what is the input? What's the output? And basically, what sort of math algorithm at a high level is it doing? It's doing. I know it's doing stuff with quaternion, so I'm thinking 4x4 matrices, and then doing stuff with gradient descent. So that's calculating partial derivatives and stuff like that. It's like not so much important to actually understand all the pieces, but it's just like input and output, and then basically what sort of processing is being done, because it's like when you're doing embedded, it's those three things: the input and output, and how the input's transformed to make the output. It's really like kind of like machine learning, sort of a black box, and it's like you just need to understand inputs and outputs and what's going on. What do you need to implement the in between stuff without actually trying to understand, like, okay, how does this equation get derived and stuff like that. So that's how I'm coming at it. I'm always thinking high level, and then if I need to go into the details, I will. Other things, it's like I don't bother, because you have to pick your battles too, because you just spend all day reading up on the theory books and everything too, which like I kind of got into that with the Kalman filter, and then I was just like, is there no point in understanding like the complete theory, because it's like we're doing a single application, right, for this odometry. So
for this project, definitely. Yeah, for this project, totally.
Yeah, but it's like you can spend all day reading the textbook, but it's just like you really just need to understand how you can code it and see, and what kind of microcontroller you need. One with a floating point unit, obviously, and basically optimizations that you can do to make sure that like the math doesn't take forever.
That is fascinating, man. Yeah. I'm very much looking forward to seeing where this goes and how this works out for you on the real world robot, man.
Yeah. So next week I'm hoping to maybe have a digital twin. So again, I'll share the code, right, and people can play around with it. So again, you don't even need the hardware or anything. You can have something that's like I said, it's going to be somewhat realistic, because the whole idea with the sensor fusion is it's like if there's no noise, then you won't even have to do it at all. If there's no noise or drift and all those other real world things that you get from these sensors, then you just won't even have to do these things at all. So in my digital twin, I'm certainly going to have like all the real world things that you would see, like noise and drift and bias and just like latencies and stuff like that.
Is it possible for you to pull out that my local IP address? That would be really helpful. I didn't realize that was on the screen.
On my video that I released, I'll make sure to clip the IP address that I had up. It shouldn't have been longer than just a couple of seconds, but okay. Then we'll have that full SLAM explanation.
Cool.
Everyone get a port scanner and scan that IP address, and
Heck no. My Fortinet will be going up like crazy.
Well, you shouldn't be worried. You got one of the best firewalls that their money can buy.
Yeah.
Well, I guess you can have a firewall, but you have to make sure you configure it right. And I can actually say, for me, I not necessarily probably configured it correctly either for my OpenSense one.
Right.
I do have to head out right about now to get ready for work, and I will, as always, share the link. To the video once it's released.
Yeah. Also put the link to the YouTube video on SLAM, and then also the thing on the Magic filter too, so people have that. Certainly, I should create. Maybe next week I'll create like a documentation page somewhere, like on GitHub pages or whatever.
God bless you, man. Yeah, that's excellent.
All right. Well, see you all next week. Man.
See you next week, Josephine. Next week, we will be focusing on making you get the robot ready. I heard the opportunity to hear what Eric's doing, and it's so it's so
Yeah.
pertinent to what we're going to be doing that I figured, let's focus on this for today. But next week we're building those robots, man.
Yeah, and mine is almost done. I just got to get everything basically connected to the chassis. Like
You can
I
do
have.
that if you can get that done before next week, Josephine. Feel free to message me or call me or whatever while you're doing it, and I'll help you get it done. Because it would be great if, and you too, that goes for you too, Joe. If you guys can have that physical robots together, so that next week we're dealing with just software, we're going to be driving your robots around next week.
Cool.
Yeah, and I have to make sure that I actually successfully installed Ubuntu onto my Raspberry Pi.
Easy.
Yeah,
Make sure
really
you use
easy part.
Raspberry Pi Imager and set
Yeah,
your SSH
I used-
credentials.
I did use the imager and I installed the SD card, but I haven't actually powered on the Pi yet. So I just needed to do that to make sure that it's actually installed and working.
A good way to get familiar with that, plug in. I'm sure that you have. If you don't, then definitely get one. HDMI to micro HDMI, so you can plug your Pi into your computer.
I have.
And then
I totally have.
Yeah.
Yeah, I totally.
And also
make
sure you use the headless Ubuntu. You're not going to want to have a whole Ubuntu desktop on your Pi.
All the GUI and all that crap on it. Yeah.
Yeah, exactly. Like there's no need for it. But why I want you to plug it into the TV just so you can kind of see the prompting and see everything happen in real time. That way, because obviously it's going to be working, but you've never actually seen it work, so it's good to be able to see it on the screen. But yeah, that's great. I really am happy with where we are right now.
Yeah, and
so we'll let you get to work,
Josephine.
Yeah, I hope so, man. So am I.
Well, I'll see you all later.
See you later.
God bless.
Yeah. See you, everyone.
Oh, yeah. I guess. I mean, I'm cool to continue a little bit. I'll tell you what though, it has been a pretty info heavy meeting so far. So why don't we, Eric? I would love to hear to be continued of these explanations next week. If you're able to join us next week, man. I really love what you're doing, and I'm really impressed by it, and I'm really much looking forward to seeing how it works, seeing if you can get that digital twin together. I cannot wait to see what that's going to look like. And then, and then eventually getting that onto a machine. You guys still there?
Yeah, I'm still
Is that
here.
on my end?
I don't know if Eric stepped away for a minute or not.
Possibly. Well, I'll tell you what, Joe, do you have any other questions?
The only question I have is for when I'm connecting the motors to the L298N. I don't know which order they're supposed to go in.
From the motors to okay. So this is really hard to explain, and that's the only reason I didn't I guess I could put together a diagram, but your motors are facing each other. So that means that or not positive and negative don't really apply, but for lack of a better way to explain it, you want one polarity. One polarity is going to be top on one and bottom on the other, since they're facing each other. So it's think mirror image, right? So the top and the top and the bottom are going to be connected to one channel on one side of the robot. Does that make sense?
Yeah.
Am I explaining that correctly? So those are both going to be connected to the same in A or out or in A. And then the other two, so you got these two, right? This hand's index finger and this hand's I guess index finger too. Yeah. So index fingers are going to be one channel.
Okay.
And then one polarity of one channel. And then middle fingers are going to be, those are going to be, got to be careful with the video, right? Those are going to be the other, those are going to be the other side of the other polarity. So you're going to, and let me know if I'm explaining this correctly. I'm trying to do it as best as I can. You know what? Sure. It's hard to even show you because I have the wiring here. Let me grab my other robot. The other robot's wired with better color.
Because I noticed that the L298N has, 1 through 4 outputs. So I wasn't sure.
Yeah, exactly. So 1 and 2 for one
Yeah.
side, and then 3 and 4 for the other side. That
Okay.
that will coincide with the code that is already in my program, in my software. I mean, so here you can kind of see I did red and black. It's really
Yeah.
hard to see, but if you can
Okay.
red and black, you're going to connect the 2 red ones and then the 2 black ones. The 2 red ones, so top here, bottom here, will go into one of the in one, for example, and then the
Okay.
black ones will both go into in 2. And then on the other side, the 2 red ones will go into in 3, and the 2 black ones will go into in 4. You're going to want to keep red odd and black even, or red even and black odd. And if you plug everything in and your robot's going backwards, all you have to do is switch odd and even.
Okay.
Does that make sense?
Kind of.
Yeah.
It's really hard to explain.
Yeah,
But
yeah.
you basically what you want to do, man, I wish there was an easier way to show you this. But you want to connect the same polarity of these 2 motors, and that's going to go into one of them. The other opposite polarity on those same 2 motors is going to go in the other one. So that's in 1 and in 2. And then on the other side, you're just going to duplicate that, but with the red into in 3, and then the black into in 4. And anyone who's watching who has one that says out 1, out 2, out 3, out 4, just do the same thing with out.
Yeah, that's what I have. Yeah, out 1, out 2.
Yeah, out. Yeah. That's it. It just depends on your motor controller.
Okay.
But yeah, man, I'm going to try to figure out how I can get a diagram up that explains this better, because it really is easier to see it visually. But the way that the robots are set up, like, it's really hard you can't really see it, you know?
Right.
I'm going to work on that. I'm going to get that together. Any other questions?
The only other thing I was gonna do, no, that's it. Yeah, I'm kind of Frankenstein a chassis for everything else to kind of sit on top of the current chassis of the of the robot. So
yeah, I think a pencil box would be a pretty good, like those pencil boxes everybody used in middle school. I think that would be a pretty good option because it's already made, it's cheap, and you can put some of the stuff on the bottom and some of the stuff on top. Just hot glue it on.
this is what.
That's perfect. Oh, so your thing actually came with platforms. That's perfect.
This is This is from a really old robotics kit that I have that I've been kind of dissecting and trying to figure out. Oh, this could work. I could kind of glue everything onto the top of this thing, and
Now just get 2 more screws and connect that to the base of your chassis. You'll have 2 levels. That's more than enough surface space.
Okay.
So that's perfect. And then you just have to figure out where you want to hot glue your on-off button and where you want to hot glue the fuse holder.
Right.
And then you're good, man. Then you're ready.
Awesome.
See if you can get that robot assembled before our next meeting, and feel free to call me, text me, email me if you need any help, man. Okay. And if I'm not in a meeting or if I'm not doing something, I'll be there right for you, or I'll let you know. Hey, I'll be available this day and time. And we'll find a time. If we can do that before next Thursday, we'll be just doing software, and that'll be great, man.
Awesome.
Well, I'll tell you what, I'm going to check out a little early this time too. I will see you in a week, man. Hopefully, I'll talk to you sooner than that.
Yeah, definitely. All right.
Excellent, man.
Take care, guys.
Yeah. Bye for now, guys.
All right, bye.
Livia, you there? Yeah, I assume you're probably away from your computer. If you can hear me, very much looking forward to getting that recording. This has definitely been the highest. No other meeting we've had has been this information dense. And we got a nice video of my software finally working the way that we want it to. So
awesome. So I see. I am stopping it right now, and it's going to take a second for it to actually load onto the drive.